to be able to draw one spectra and label both axes.
I hear you're going to watch Kentucky.
And then, what's a spectra?
What's a spectra?
My luck, it was small.
She thinks I'm joking.
I hope you got that.
It was been to the wine bar again.
What's the talk?
I'd like to welcome you to the national meeting of the Tri-State Catalyst Club. First of all, I'd like to thank our sponsor, Ashland Petroleum Company, for providing fine facilities and, of course, their continuing financial support of the club. Bob Bombels especially is to thank for his efforts in getting the funding for us. We have a few items of business tonight. First item is that the upcoming elections. Tonight we have an opportunity to receive nominations from the floor for 2 offices and 2 directorships. The offices are President-elect, who will have a 2-year term as President-elect and then succeed for a 2-year term as President, and Secretary-Treasurer, who has a 2-year term. Directorships are 4-year terms. All these offices and directorships will be starting this summer. For President-elect nominees that we have so far are Pat Doolin of Ashland Petroleum Company, Kathy McDonald, the former Mrs. McDonald of Union Carbide. For Secretary-Treasurer, Dave Zalewski of Ashland Petroleum Company, and Diane Milburn of Center for Applied Energy Research. And there's several people that are been nominated for directorships. At this time, I would ask if there's any nominations from the floor for the office of President-elect. Not seeing any or hearing any, we'll move on to Secretary-Treasurer. Okay, not seeing or hearing any, we'll move on to the office of the directorship. Not seeing or hearing any, we'll declare that the nominations are closed from the floor. Our continuing officers for next biannual term are Barbara Warren, who will become president. Fred Tungay will continue as secretary, as representative to the society from our club. That is a 4-year office. And we have 2 continuing directorships, Steve Augustine and Sarah Van Sant. Both these terms expire in '98. The election will be by mailed ballot. The ballots are to be returned, if by mail, to be received by May 3rd, and if presented in person at our spring symposium by Monday, May 6th at noon. There being no questions on the elections, I'll move on to the next item, which is the Founders Award nominations. These nominations closed March 1st, and we have 2 nominees, and the officers and directors will be deciding that award, which will be announced at the Tri-State Catalyst Club Spring Symposium. I'd like to ask Barbara Warren to make a brief announcement about the Spring Symposium. Barbara?
We'd like to encourage you to come to the Spring Symposium, and anyone who is planning on coming who has not yet made a reservation in Charleston, please do so, because the hotels fill up very quickly. The Marriott has a block of rooms for $93. There are cheaper hotels. That block of rooms will be released in mid-April if you haven't yet made your reservation. Also, we can accept some additional talks if you can get me the authors and the titles for the talks before Friday, and you may send the abstracts in before April 3rd. We have academic participation from Carnegie Mellon, from WVU, BPI, the University of Kentucky, Louisville, and Ohio State. So we have about equal representation representation or more equal representation in the homogeneous catalysis area. And as last year, the heterogeneous catalysis will be concentrated the first day, Monday, May 6th. The homogeneous catalysis will be concentrated May 7th. And we do encourage you to, if anybody else has any abstracts, send them in. There are a lot of students interested in coming because we're having a student poster competition. So, Ubed Ozcan, Ed Kukler, Davey Davyberger, Ted Oyama, Dave Cox, Dorothy Gibson, Andy Gelman are among those who are coming and bringing students. I'm available for any questions.
Thank you, Barbara. I just have two reminders here about upcoming meetings of interest to the club members. The first is the 11th International Congress on Catalysis in Baltimore. That's June 30th to July 5th of this year, 1996. I want to mention that the registration material has been mailed out, so if you haven't received that, you can see me afterwards and I'll give you a form on that. Also, see me if you haven't received information on the 15th meeting of the North American Catalysis Society. That will be in Chicago, May of 1997. All right, this evening we have the opportunity of hearing Professor Peter Stair of Northwestern University. He received his undergraduate degree in chemistry at Stanford University. He then did his graduate work at Berkeley under Professor Gabor Samarjai. And right after graduation, he began his position in the Northwestern University Chemistry Department. He is a past president of the Chicago Catalyst Club and a member of the Catalysis Center. His talk to us tonight is entitled A New Method for Characterization of Catalysts, Ultraviolet Resonance Raman Spectroscopy. Without further introduction, I present to you Professor Peter Stair.
So I'm going to change the title just a little bit. I want to thank the organizers for inviting me to come and speak to you tonight. I'm going to tell you a story that I'm very excited about. I'm more excited about this piece of work and what we're doing now than anything I've done in science so far, and I think that this will represent perhaps the most significant thing that I ever do in my career. So I'm having a good time telling people about it because I really like it, and I think that the response that I've gotten from everyone so far that I've told about it has been very positive. Some of you may know me from work that I've done at Berkeley and later at Northwestern, working on single crystals and ultra-high vacuum. So this work using Raman spectroscopy is the first time we ever looked at a real catalyst. And we actually have looked at real catalysts in the sense of something out of a refinery reactor. We can't get any more real than that, I guess. But what I want to do here to begin with is just to go through just a little brief background on Raman scattering, just to remind you what it is, and then to highlight one of the particular problems in Raman scattering that we seem to have overcome by using ultraviolet light as the excitation for the Raman scattering. Okay, so generically what happens in Raman scattering is we have some solid, and we have a laser. Typically it's in the green, a green laser, which would come in and scatter off the sample. Of course, most of the light that scatters off the sample is green, but a very small fraction of the light will come out at different colors from the green. And you'll see a pattern of peaks appearing at longer wavelengths from the green that are shifted by energies corresponding to vibrational quantum. And so it's a method for measuring the vibrational spectrum of a sample, analogous to infrared spectroscopy, which measures the vibrational spectrum of a sample. Now, Raman scattering has some features in common with infrared. It provides chemical and structural information like infrared does. It has a wider range of vibrational frequencies that it has accessible to it. In particular, it can look at very low vibrational frequencies as well as energy associated with very large vibrational energies. Since it's a scattering technique, the information that you obtain is from some skin depth, which typically in the visible is about 300 nanometers. So you're getting some primarily bulk information, but with some biasing towards the surface. It has, in principle, advantages over infrared in that one can look at hot samples. With infrared, it's difficult to look at hot samples because the luminescence from the sample, the infrared radiation from the sample, often will mask the infrared spectrum. So in principle, one could use this as a technique to look at real catalysts. Now, if you look in the literature of the application of Raman spectroscopy to catalysis, you find that most of the work has been concentrated in a few kinds of studies. People have looked at the formation of catalysts from the precursors, or they've looked at the catalyst after calcination, or they've looked at supported oxides in particular, where the oxide active phase may be a strong Raman scatterer, and the support, such as a silica or an alumina, is a very weak Raman scatterer, so you can see the active phase. But if you look for studies where people have tried to look at catalysts that are actually working, you find almost none. And there's two reasons for that. The first one is that the signals in Raman scattering are very weak. So on this little diagram up here, I have to attenuate my green light that scatters from the sample by a factor of 10 million to get it on the same scale as the peaks from the Raman scattering. So these are very small intensities. And the other problem, which is really the main one for application of Raman scattering to hydrocarbon catalysis, is the problem of fluorescence. Typically, when you look at or very often, when you look at a catalyst sample and try to measure the Raman spectrum, you get something that looks like this. So this is a spectrum from a deactivated rhodium on alumina catalyst. So this catalyst has been coked. This is a sample that I got from one of my friends in Amoco. And all you see in the spectrum is just a broad background of fluorescence. And you see no indication, essentially at all, of any nice sharp peaks that you would expect for a vibrational transition in the catalyst. And the problem here is that the typical molecules which are produced in a hydrocarbon reaction that form coke cause this fluorescence, so that virtually any catalytic reaction involving hydrocarbons is a problem to study with Raman spectroscopy. The only exception to that are oxidation reactions, where you have oxygen to burn the coke off the catalyst. And there have been some in situ studies done, in particular by Knutzinger and by Lunsford, looking at oxidation catalysts. This fluorescence is very strong. This is just an excerpt from a book by Stencil that he wrote about Raman spectroscopy applied to catalysis. And he says here that the intensity of the latter, namely the fluorescence, can be as much as 10 to the 4th times greater than the Raman signal, so that you have a very difficult time then pulling this tiny signal out of this fluorescence. Now, a great deal of work has been done to try to avoid or find ways to get around this fluorescence problem. And one way, which has been discussed in a very nice book by Ferraro and Nakamoto on an introductory text on Raman spectroscopy, is to use near-infrared radiation as the excitation source. So instead of using visible excitation, where the photons have enough energy to produce this fluorescence, one uses photons with very small energies that are not able to excite the fluorescence because they're simply not able to produce the electronic transition in the sample that you need in order to have fluorescence. So this is just a table or a little graphic from the by Ferraro and Nakamoto. It talks about the advantages of so-called FT Raman, which is near-infrared Raman. And they comment on the fact that it reduces or eliminates fluorescence. But then they also say that there are some disadvantages. In particular, oftentimes you have absorption in the near IR, so that if you're looking at a colored sample, you can't do Raman scattering from it because of this absorption. Another problem is that the Raman scattering intensity goes as the fourth power, a very strong power in the frequency of the light that you're using to excite the sample. So that when you go from the visible to the near IR, where you are lowering the frequency by a substantial amount, you're also killing off your Raman scattering because of this due to the fourth dependence. Okay. Now, about 10 years ago, a fellow by the name of Sandy Asher at the University of Pittsburgh got another idea. And his idea for avoiding the fluorescence is shown schematically in this diagram. So, in the normal case, one excites Raman scattering with respect to the fluorescence that a sample has produced in such a fashion that the Raman peaks are buried by the fluorescence. And in the near IR experiment, the excitation takes place over here, where we're avoiding the fluorescence. Well, Asher's idea was, let's go over on this side of the fluorescence, and let's excite the Raman scattering at such a short wavelength that all the Raman peaks will appear before the fluorescence starts. The advantage of this is that you don't have this problem of losing intensity due to the fourth dependence. In fact, you enhance your intensity by the due to the fourth dependence. And secondly, if one is interested in looking at a hot sample, you don't have the problem of interference from the luminescence because all of your detection and everything is done at such short wavelengths, such high energies, that the luminescence is very small in that high energy region. So where do we need to go in order to be able to get below the typical fluorescence that we might expect for coke on a catalyst surface? Well, so Asher looked at this, and what I have here is a transparency that shows the absorption or excitation spectrum as well as the fluorescence spectrum for a series of 4 molecules that are sort of generic representations of what you might expect coke on a catalyst to look like. So here's naphthalene and anthracene and phenanthrene and something else that I don't know the name of, but anyway, it has 4 rings fused together. And what you can see here is that the onset of fluorescence, the low wavelength onset of fluorescence for all of these guys is about 300 nanometers. So that if the excitation was done at about 250 nanometers, all of the Raman scattered light would appear in the region from about 250 to about 280 nanometers, and so we would avoid the fluorescence from any of these kinds of molecules. So 10 years ago, he did the experiment using a pulsed laser system to generate the UV, and he made a measurement on a coal liquid. He had to look at the liquid in a jet because the pulsed laser beats the daylights out of the sample because of the fact that there are very high powers in each of the laser pulses hitting the sample. But with the coal liquid in the jet, he was simply looking at a new sample every time he fired his laser. And he obtained a quite nice spectrum from this sort of black, ugly-looking coal liquid. Quite a feat, actually, to get any kind of a Raman spectrum at all. Now, I found out about Asher's work about 3 or 4 years ago, something like that. And we had tried to do some Raman spectroscopy on single crystals with not too much success. But we had all of the equipment from that attempt that we had made to measure a Raman spectrum. But in addition to the equipment that we had available to us previously from doing Raman scattering, we started another series of experiments where we had a very strong green UV laser, green argon ion laser, that we were frequency doubling to produce ultraviolet light at 257 nanometers that we were using for photochemistry. So we weren't doing any Raman scattering with this, but we were using it to do photochemistry. And after reading Asher's papers, I thought to myself, we ought to try this experiment, because now we have light just in the wavelength range that he says we need, and we have all of the spectrometer and all of that stuff to do the Raman scattering. And I can't remember exactly when I thought we should do this, but it was at least 3 or 4 years ago. And then it took a while to sort of find the right set of conditions, that is the right person to do the work, and an opportunity to free up this laser system from doing photochemistry so we could try the Raman experiment. And so anyway, in the summer of 1994, the Catalysis Center agreed to sponsor and give me some seed funding to try this experiment. Now, at the same time, in 1994, there was a visiting scholar from China who was working with Harold Kuhn, who asked me who knew I wanted to try this experiment, and asked me if there was any possibility that I could support him for an extra year so that he could stay here and try this experiment. So we wrote a PRF proposal together, and it was funded, and so he was able to work with me for 95, and he's actually stayed on and will finally go back to China after the international meeting in June. So he and this graduate student set this experiment up. And just to give you an example of sort of the first spectrum that we ever measured. So the first thing you do is you measure something easy. And this is just an example of a spectrum of acetone that we measured. The resolution at the time when we were measuring this spectrum was about 22 wave numbers. So it isn't terrific, but at least it's in the vibrational resolution regime. And of course we get a nice pattern of peaks from acetone, and it looks something like the literature spectrum for acetone. Now, it was Lee's idea, and it was actually his idea put forth in the PRF proposal, that what we really should do is we should try to use this technique to look at deeply colored materials. So as he put it, and I told people this morning, his comment was that if we can look at black catalysts, people will be interested. And so he asked me if I could get a hold of some black catalysts. And so I called up my friend Frank Modica at Amoco, and I asked him if he had any black catalysts. He said, lots of black catalysts. And I said, do you want? And he said, well, just give me a selection. I explained to him what we were trying to do, so he sent me a whole range of things. And one of the catalysts was this rhodium monoaluminum catalyst that I showed you. So here's the spectrum again, where we just see the broad fluorescence from the sample by excitation in the green. But when we do the excitation in the UV, we get a beautiful Raman spectrum. It's just, it's hard for me to explain how pleased and surprised I was that it worked this well. I mean, usually things don't work out so well. It took about 10 minutes to get a Raman spectrum that looks like this. Okay, so we have very nice signal to noise, and these bands here are associated with the coke on the supported catalyst. Well, so we wanted to be sure that this wasn't a fluke, and so we looked at the other samples that they gave us, and this is just a representation. This just shows 3 different ones, including the rhodium monoalumina. There was also a beta silica and a fluid cracking unit catalyst, and this is what you see in the green. That is, you see nothing, you just see fluorescence. And when you look at these samples in the UV, you get beautiful Raman spectra every time. So that's just an example. So here we're seeing coke on these catalysts. Each of these spectra took about 10 minutes to measure. We get very nice signal to noise. And I can tell you that we have seen a Raman spectrum from every sample we've measured. And it's well over 100 now. So we've gone from a situation where the technique hardly ever worked on coke-covered surfaces to one where it always works, and we always get a spectrum. Now there are cases where the scattering is weak, just because the Raman scattering is weak from the sample, but we always are never done in by fluorescence. So the major obstacle to using Raman scattering and catalysis is gone, and it is now, I think, quite a very useful tool. Okay, so one of the things that we were interested in, of course, is to learn what sort of information we could get from this Raman scattering and what kinds of samples we could look at. And one of the things that I'm going to talk about here is the interesting subtle differences that occur in the position of this main coke band we see. So there is a real and reproducible shift in the position of this coke band on these different catalysts. And so that must mean something in terms of the nature of the coke on these catalysts. And one of the things that we wanted to do was to learn something about what that meant. Now, before I do that, though, I just want to give you a flavor for some of the other things that we've looked at. This is a diamond, CVD diamond film that we've looked at. You can imagine that once we found out this worked, we wanted to measure every sample we could get our hands on, right? And we were just asking people to give us samples so that we could see if it would work. And it's sort of like the kid in the candy store situation. So here's an example of what happens when you try to look at this diamond film using excitation in the blue. You basically don't see anything. When you do the UV, you see a nice strong diamond band, and you also see the amorphous carbon which is around. The only thing that is appearing in this case is fluorescence. We looked at a grease sample. Grease fluoresces tremendously. I mean, it's not like these samples don't fluoresce. I mean, as soon as you hit, for example, the grease sample with the UV beam, it fluoresces like mad. You can see tremendous amounts of light coming out of the sample, but it's all at the wavelength that it doesn't bother us. Okay, there's just an example of a grease sample. So you get a nice, strong Raman. In fact, grease gives us one of the strongest Raman spectra that we've seen. We've also looked at a supported oxide catalyst. This is a catalyst that we got from Harold Pung's group. We wanted to compare the sensitivity of our instrument to one that he has in his laboratory. This is a very low weight load, vanadium weight loading of VPO on silica. And Harold can't see anything in his spectrometer. But in our spectrometer, we can get a nice spectrum characteristic of the VPO species on the surface, and you can see it even changes as the phosphorus-vanadium ratio changes. So it seems like this is a very nice way of looking at catalysts. So now let's go back to this question of the coke. Now, we know, the catalyst community, I guess, or maybe the French most of all, know something about how, this is the Chinese spelling for olefin, how coke forms on a catalyst. If we start out with a saturated hydrocarbon, the usual progression that is thought is that you make an unsaturated hydrocarbon, or you may have some unsaturated hydrocarbon contaminant in your feed. It forms a polyolefin. The olefins cyclize into aromatics. They fuse together into polyaromatics, and then you form sort of what is either called graphite, pre-graphite, or microcrystalline graphite, then eventually amorphous graphite, and finally crystalline graphite if you go long enough. So we thought that by using this scheme and looking at coking, starting with an olefin, a simple olefin, that we might be able to deduce what the shifts in that coke band mean in terms of the nature of the coke on the catalyst. So we're basically using what's already known about coking as a way of diagnosing what these shifts mean. So in order to do this, you need some way of coking your catalyst in a controlled way. So Lee built a little simple Raman reaction cell here. So this is just a quartz cell. We have a little quartz tube here, which is about 1/4 of an inch in diameter, and we just mount a catalyst pellet across the end of the tube. We have a gas flow that goes through the pellet and back out through an exit, and then we can simply move this back and forth between a heated region where we can coke and a measurement region where we can make a measurement. So it's a controlled atmosphere cell. So now, just to sort of orient you in terms of where we might expect coke bands to be, let's look first at graphite and see where that is. Okay, so here's the Raman spectrum that we get from graphite. And you get a very nice Raman spectrum. There's this peak out here is basically an overtone of the graphite vibrations. And this strong Raman scattering peak here at 1575 is very classic for highly crystalline graphite. Now you remember the other bands that we saw were up above 1600, so they're in a completely different spectral range than this. So they really are not graphite. We don't know that right away, basically just by making that simple comparison. So in terms of thinking about a system or systems to look at to follow this coking, I have benefited immensely from conversations with Frank Modica and Jeff Miller at Amoco. And what they suggested is, why don't we give you two zeolites, a ZSM5 that doesn't coke very easily, and a USY that cokes like mad. And why don't you try propylene coking on these two catalysts, zeolites, and why don't you see if you can see the difference from doing the Raman spectroscopy? So that sounded like a pretty good idea. And so first I'll show you the spectra that we got from coking with propylene now on ZSM5. Okay, so the first spectrum here, so how do we do this? Well, we just expose the sample at room temperature to propylene and helium, then we purge with helium, and then we take a look at it. And this is what we see. So this is not propylene anymore. So already at room temperature on this catalyst, the propylene has formed a layer which doesn't come off in helium. And if you look at the positions of these bands, so we're looking at this both the CH region and the CC stretch region, this is characteristic of what one might expect for a polyolefin on the surface. So, in fact, Frank and Jeff already knew that this was what would happen because they'd done the carbon-13 NMR on just exactly the same condition, and they wanted to find out if we could get the right answer, if you will. So we did. We got the right answer, and we see this polyolefin on the surface. The one band that we don't know what it is in the spectrum is this band at 1560, and it isn't always there, so at least for this discussion, I'm going to ignore it. All right, so now what we do is we take the material and we heat it at 500 degrees C for an hour in propylene and helium. So we're really trying to coke it up. And basically what you see is that there's some change in the carbon to hydrogen ratio based on the fact that the CC stretch region bands have grown and the CH stretch region bands are about the same intensity as they were before. But basically not too much has happened after an hour at 500 C. Now if you go over 3 hours at 500 C, then you get the spectrum shown here with C. Clearly some changes have taken place in the nature of the coke. We've lost hydrogen, and this band here, which was at 1635, has shifted to 1625, so it's shifted down. This spectral position is about what you'd expect for aromatic on the surface, for the ring breathing modes or the CC stretches in aromatics absorbed on the catalyst. If we then just remove the propylene from the feed altogether and just purge in helium at 500 degrees, then basically virtually everything comes off the sample except for some small residual band here at 1615 wavelengths, so which is shifted down somewhat more from 1625. This band position is representative of what we would expect for polyaromatic type of coke on the surface. So that there is a fraction, a relatively small fraction of the coke on the ZSM5, which is polyaromatic and doesn't come off, but the majority just comes off by heating and helium. So it's what you'd expect for a zeolite which is resistant to coking. The coke comes right off. All right, so now let's compare this to the USY, which is known to be less resistant to coking. Okay, so there's a very strong difference in the way the spectra go. First of all, at room temperature, so this is just the room temperature propylene absorption. This spectrum is essentially identical to the ZSM5 spectrum. You can see that the background rises here, and so we do get some fluorescence. We don't get away from it entirely, but it doesn't kill us in terms of being able to measure the spectrum. But if I flatten this background out so that it looks like the ZSM5 case, and I lay this spectrum on top of the ZSM5 spectrum, they just lay right on top of each other. The shapes of the bands and everything are identical. So it's the same stuff at room temperature. But now, if we heat not at 500 degrees C, but only at 300 degrees C for 1 hour in propylene helium, we have a vastly different spectrum. And we have a vastly different spectrum from what we saw with the USY, or sorry, with the ZSM5. Remember with the ZSM5 at 500 C for an hour, there was hardly any change in the spectrum at all. Here, we've lost most of the hydrogen. We've experienced a substantial shift in the position of this band in the CC stretch region, so that now we're in the polynuclear aromatic region already at 300 degrees C. And if we then go to 500 degrees C, so that we mimic the treatment that we gave the ZSM5, there's essentially no hydrogen left at all in this spectrum. And the CC stretch peak has shifted down below 600 wave numbers. In fact, if you look at this spectrum and compare it to spectra for microcrystalline or poorly ordered graphite, they look very similar. So already at 500 degrees C for an hour, the USY has made microcrystalline graphite, whereas the ZSM5 did not. So of course we were very pleased, because that's exactly what we hoped we would see. If you go longer, that peak, that coke band peak, shifts even lower. And now we get a spectrum here after 5 hours at 500 degrees C, which looks like almost a literature spectrum for microcrystalline graphite, or defective graphite. This band over here at 1365, you might remember that the graphite spectrum was very clean. There was just one peak. This is characteristic of vibrations that are associated with the edges of the graphite planes. And this very strong band then showing up at 1585. Now, of course, the other thing you can do is you can try burning the coke off. And we were interested to see what we would find out, what we would see in the Raman spectrum as we were burning the coke off. So the two bottom spectra here show the result of burning the coke off. So the first one is at 500 degrees C for an hour. And what you can see is that you lose a substantial amount of the carbon from the surface based on the attenuation of this CC stretching peak. But the other thing that's interesting is that the peak is shifted. So that originally it was at 1585, and now it's shifting up to 1610. Finally, if we go at 600 degrees C for another hour, then we remove most of the coke from the catalyst, and we end up with a peak which is at this 1615 wave number position, similar to what we found with the ZSM5. Now, I showed these data to Bob Byerline when he came to visit us last fall. And Bob, when he was at Amoco, did some Raman studies of coke. And he was very interested in the fact that the positions where these bands showed up, and the fact that they seem like they end up in this aromatic or only a few rings fused together aromatic type structure. So his thought, which seems reasonable to me, is that when you burn this coke, the graphite planes essentially burn preferentially from the edges, so that the graphite planes are shrinking from the edge. And what you ultimately end up with, in the end, is some planes which for some reason are not attacked by the oxygen. Either they're inaccessible or they're bound in some interesting way so that they are not oxidized. But the idea would be that this represents a few fused rings, maybe even just 2 or 3, but with no hydrogens. So that this is a form of carbon which is not stable by itself, but is only, because normally you'd have hydrogens terminating a naphthalene or an anthracene type molecule, but must only exist on the catalyst surface. Now, I like that idea. That's his idea, not mine. I like that idea, but I can't prove it at this point. Now, we thought it would be interesting to compare these results to a catalyst which does not have the acid sites that either the ZSM5 or the USY have. And so we also looked at a platinum alumina catalyst. This is again, this catalyst came to us from Amoco. It was coked originally, but we cleaned it off by burning the coke off in oxygen. Okay, so this is again propylene exposure. Okay, so here's what you see before you do any propylene exposure. Here's the room temperature propylene exposure. We don't have these coke bands on this catalyst. So we don't have the room temperature polymerization that occurs on the acid catalyst, and that seems quite reasonable. We don't have acid catalyzed polymerization, so we don't have acid sites. If, on the other hand, we continue to expose to propylene and we heat, we eventually develop a coke band, which ends up giving us a spectrum that looks like this, where this peak is at 1600 wave numbers, so that's characteristic of polynuclear aromatic structure on the surface, but not pre-graphite. So pre-graphite we would assign, based on what we know about coke chemistry, to give us a band below 1600 wave numbers, and this one then gives us a different kind of coke than what we see on the acid catalyst. And of course you can oxidize it off and it all comes off. So what we find here is that with the Raman scattering, we can rather quickly and easily discriminate different kinds or classes of coke on the catalyst. So the perfect graphite gives us a single band at 1575. The sort of pre-graphite or microcrystalline graphite gives us bands down as low as 1575, and also this so-called defect band at 1360. The polyaromatic gives us a band around 1600 or maybe a little above. Aromatic up around 1610, so this would be mononuclear aromatic. And then the olefinic gives us bands at 1620 and above. So I think we have a nice way then of characterizing coke on catalysts. So in thinking about another interesting catalytic system to look at, I was persuaded by my colleague Wolfgang Zockler that the interesting sulfated zirconia catalyst would be an interesting material to look at. Of course, I've talked to a number of people here today that work on sulfated zirconia, so I don't need to tell you why people are interested in it for butane isomerization. But of course it has the problem that it dies very quickly. And of course the assumption is that it dies, or one of the assumptions has been that it dies by making coke, because of course that's what acid catalysts typically do, and acid catalysis is what one would expect for a skeletal isomerization reaction. Even though I think that Wolfgang Zockler has shown quite convincingly that at least for butane, that's not the mechanism for the sulfated zirconia. But in any case, we thought we have a very nice way of looking at coke. Let's look at this catalyst system and see what we can learn. Okay, so just to motivate the reasons for doing the UV Raman scattering, it is possible to do normal Raman scattering on the sulfated zirconia, although it's not easy. Helmut Knutzinger has published some Raman spectra for the sulfated zirconia, and if you look at his data, it's clear that he had a fluorescence problem and that he had a difficult time pulling the peaks out of the data. And that's not surprising when you look at the spectrum that you get for normal green excitation from a fresh sulfated zirconia and a used sulfated zirconia. So you can't tell very much from this spectrum. It's surprising in a way because if you just look at zirconia itself without the sulfate groups, then you get a very nice Raman spectrum. And this is what we get from a sample of zirconia. And this pattern of peaks is representative of the so-called monoclinic form of zirconia, which is the stable form of zirconia at low temperatures. Okay, so we went ahead and measured the Raman spectrum from using the UV excitation for the sulfated zirconia, and the result we get is summarized in this transparency. Okay, so here's the fresh sulfated zirconia. I should say that we got these samples from Zockler's group. They did all of the reaction work on them, so the deactivated catalyst was deactivated by them, and they just gave it to us, and then we looked at it in the air. So here's a fresh catalyst. These bands here are characteristic of the sulfate groups. So this region here is characteristic of a sulfur-oxygen double bond, and this band here is characteristic of a bridging oxygen between sulfurs. These peaks here are what we would expect for the position and intensity ratio of peaks from the tetragonal form of zirconia. And it's known, actually, that you need the tetragonal form of zirconia to have an active catalyst, the sulfated tetragonal form of zirconia. There's some other interesting bands here that we don't know what they mean at this point, but they're in the zirconia region. All right, so that's the fresh catalyst. Now we take the used catalyst. This has now been deactivated by a reaction in butane. Now, the first thing that we notice from this is that there's no coke band on this catalyst. There's no band at 1600 wave numbers. And after we made these measurements, I told Zockler about this, and he said, well, we better do a temperature program of oxidation and see how much carbon we find on the surface. And sure enough, there's very little carbon on this dead catalyst. So this catalyst died, but it did not die because it was coked, because there's no coke. Okay, but what we do find is that if we look at the spectral region here, we see there have been some pronounced changes in the spectral region down here, which is representative of the zirconia. And in fact, if we compare the spectrum that we measured for the dead catalyst with the monoclinic form of the zirconia, we have almost an identical pattern of intensities between the dead catalyst and the monoclinic form of zirconia, which is known to be the inactive form of zirconia. So what we seem to have seen here is a transformation between the tetragonal form and the monoclinic form of zirconia, and that in fact is why this catalyst died rather than that the catalyst was coked. Well, okay, now normally you can regenerate the sulfated zirconia by oxidation. And typically you would expect that that burns coke off the catalyst. That certainly is what I would expect. But now we have a situation where we don't have any coke. So what would heating and oxygen do? Well, so here's an example of a spectrum that was measured after exposure to oxygen at 500 degrees C. And there's a couple of things that you can notice here. One of the things that you notice is that the intensity in the region corresponding to the sulfur-oxygen double bond is increasing between the used and the regenerated catalyst. The other thing that we notice is that the pattern of peak intensities, these two peaks in particular, are transforming from an intensity pattern which is representative of the monoclinic form of zirconia back towards the form for the tetragonal zirconia. We tried to look at this more carefully, and in fact, we used then this little controlled atmosphere cell that we had to look at this regeneration process. Now, with this instrument that we have, that I showed you early on, and that we made all these measurements with, we have a very difficult time looking at low Raman shifts. And it just has to do, it's a technical matter that has to do with a filter that we're using to remove the elastically scattered light from the sample. So what we see here is a progression of time of the sulfated zirconia being oxidized at 500 degrees C. And this spectrum here is representative of the monoclinic form of zirconia. And as we heat the catalyst, we ultimately go through some transition forms, which don't seem to correspond to any crystalline phase of zirconia that we know of, but we ultimately end up, at least with the right number of peaks, and even these two peaks down here, which are quite diagnostic of the tetragonal form of zirconia. So it appears as though oxidation can transform the zirconia from the inactive monoclinic phase to the more active or to the active tetragonal phase, the sulfated zirconia. So we then, on the basis of this, propose a model that involves then a surface transformation of the zirconia under reaction conditions from a case where both the surface and bulk phases are tetragonal form to a case where the surface phase is now in the monoclinic form, possibly because the sulfate groups are reduced, or there's clearly some interaction between the sulfate groups and the zirconia. And then the oxidation returns the zirconia back to the tetragonal phase. Okay, now the story isn't over, and the story is still in progress at this point. The spectra that we obtained with this first instrument are clearly not as convincing as they ought to be in terms of this phase transformation back and forth. And the real problem is that we could not see very well at all the low frequency bands that are really diagnostic of the cope. So to get around that problem, we needed a new instrument. And so this just shows the same instrument again. The primary thing that we needed to do was to get rid of this filter that we were using to remove most of the elastically scattered light from the sample. So the way to do that is to use a different spectrometer. And the type of instrument that we need and that we actually now have is a 3-grading instrument. I won't bore you with this diagram. Basically, this part of the instrument serves the purpose that the filter served previously. And it allows us to remove the elastically scattered light while at the same time getting very close to the exciting light. There's some other advantages that it has in terms of alignment and other technical issues associated with doing the Raman scatter. We've looked again at the same samples that we obtained from Zockler's group using this new instrument. The data now are very convincing, at least in terms of the fresh and dead catalyst that he provided us with. This is monoclinic zirconia. This is the used catalyst, and this is the fresh catalyst. In particular, there's a band here at 270 wave numbers, which is only present in the tetragonal form, and you see quite clearly that it goes away in the formation of the dead catalyst, and that we get essentially precisely the same pattern of peak intensities that are observed for the standard monoclinic zirconium spectrum, or zirconia spectrum. Now, the question then that remains is what happens if we try to do a regeneration? Do we make the tetragonal form from the regeneration process? And I can't tell you the answer to that. What I can tell you is that we tried the experiment, but the butane that we were using had some olefin in it, and we produced coke on the catalyst. And the catalyst died, and the coke was thick enough that we couldn't tell whether we'd made the monoclinic form or not. When we did the regeneration, we indeed had tetragonal zirconia at the end, but I can't tell you at this point whether that regeneration just burned coke off the catalyst or whether it actually underwent this transformation. We found out that the reason that we had the olefin in the butane is that there's an extra trap that we need in the feed line that Zockler doesn't mention in any of his papers, that we didn't find out until we had a meeting with the student that actually did the work, and she just mentioned, oh yes, what about the zeolite trap? Oh, what zeolite trap? We all sort of laughed about the fact that it was a good thing she hadn't left for her job so that we could talk to her before this happened. In the meantime, that meeting was 2 weeks ago. In the meantime, Dr. Lee has been trying to run through our backlog of samples that people have given us to look at for them. We've looked at some coke catalysts from Air Products. We've looked at some proprietary catalysts from, and he told me today that they're sulfated zirconia catalysts that were given to us. We also have looked at some carbon electrodes. So the carbon electrodes are the blackest sample we've looked at. What he told me was that he gets beautiful spectra from the carbon electrodes, although the spectra are somewhat weak because of absorption. But even though the samples are strongly absorbing, it doesn't prevent us from measuring the Raman spectrum of these samples. Now, it seems to me that the real power of this technique will be in its ability to look at reactions in situ. Not in situ where you pump out the gas phase and then look at the catalyst. I would call that controlled atmosphere. I mean really in situ, where you're actually looking at the catalyst while it's a working catalyst. So we have a new cell that we made. And now we have the furnace up where the catalyst pellet is. And so we can heat the catalyst and we can run the catalytic reaction under reaction conditions. He's looked at the sulfated zirconia catalyst when the catalysts were at 500 degrees C in the pre-treatment oxidation. He's looked at them at 180 degrees C when we were coking them up with our contaminated butane. You could see the coke band grow in as a function of time. He could follow the transformation of the coke as a function of time online under reaction conditions. I think that our only limitations in terms of reaching reaction conditions are the stability of quartz to heating, which is pretty good, and whatever pressure we can tolerate across the quartz wall. So obviously there's a lot of high pressure stuff that we would have a hard time looking at, but I think there are a number of reactions that could be usefully looked at with this simple cell. Let me also say that it's no harder for us to measure a sample in this cell than it is out in the air. So all of the technical problems that have always made in situ measurements so difficult are gone. It's easy to measure a Raman spectrum in situ from a working catalyst. Okay, so let me just conclude here. By saying that Raman spectroscopy provides chemically specific information about catalytically active surface phases and adsorbed layers. So we can see these get the Raman spectrum and see the Raman active phases that we are made on the catalyst. I think that the UV Raman is going to be a really major advance for spectroscopic characterization of catalysts. Primarily, I think, because it looks to be so easy to do in situ measurements using the UV Raman. And of course, we've demonstrated that it looks like a good way to monitor coking of catalysts and probably other things as well. Let me just conclude finally with some acknowledgments of the people that really did the work. I cannot say enough good things about Con Lee. Con Lee is he's a full professor at the Dalian Institute of Chemical Physics in China. He's the youngest full professor ever in the Chinese academic system. He's one of the best scientists in China. And I'm just really fortunate that he happened to be at Northwestern and that I was able to support him so he could stay for an extra year. And of course, he's been delighted. I've never seen anybody more excited. He would call me, the first time he got a Raman spectrum from Coke, he called me at 11:30 at night at home. He was so excited. And of course, he got me all excited, and I couldn't go to sleep after that. But it's really a wonderful experience to work with someone like him. Vic Hobart was a graduate student who knew how to generate the UV and was able to help us set the spectrometer up. Frank Modica and Jeff Miller at Amoco really helped me tremendously in terms, because they know catalysis, and as a surface science guy, I don't. I'm starting to learn a little bit of catalysis. Valeria Adeyeva and Wolfgang Zockler for providing the motivation and the sulfated zirconia samples, and these people for paying the bills. In particular, the Catalysis Center and the PRF for paying the salaries, and the Air Force and the NSF for over a period of 10 or 15 years letting us buy bits and pieces of this instrument that we were able to put together and make these measurements that I'm very excited about. Thank you very much for coming on a snowy day and night to listen to me, and I was very pleased that I could talk to you.
X-ray diffraction of the monoclinic and the tetragonal samples to see whether that could show the differences that you can see via your technique?
The X-ray scattering of the used zirconia shows that it looks to be still predominantly tetragonal, but with some monoclinic. So what we think is that the monoclinic's all on the surface, and that's why we don't see the tetragonal. And of course the X-ray just sees some average of both the surface and bulk phases.
That's what I was going to ask you
Yeah.
next. Can you detect surface species contrary to the bulk?
I think that in fact we are surface selective. One of the issues that I don't have an answer for is how deep into the catalyst we actually see. We clearly see a thinner skin than what is the case for visible excitation because the UV is absorbed so strongly by most of these materials that we're looking at. And in fact, it doesn't take very much coat, for instance, on these zeolites before we don't see the zeolite anymore. We just see the coat. I need to do some simple calculations. In fact, one of the things that I did when I was in Atlanta was to get into CAS online and find some papers that provide optical constants for graphite and amorphous carbon films so that I can take those optical constants and calculate a penetration depth or an escape depth to the UV light. But I suspect that what we're going to find is that we're sampling about the first 1 to 200 angstroms is all. So there's some disadvantages to that. If you have a porous catalyst, you're not going to see into the pores very well. You're only going to see the pores that are within the top 100 angstroms or so, or 200 angstroms of the outer surface of the material. But I suspect that even then, one can learn a good deal about even chemistry that goes on in the pores. I think that's deep enough in many cases to see what you need to see.
So you said Professor Zackler found a whole lot less coke on the sulfur zirconia sample compared to the zeolite. How much less coke? Is it 10%?
Okay. What I can give you is I can give you a number that corresponds to the number of carbon atoms per sulfate group that he found. So the titration of the number of carbon. And the ratio there was about 7%. So the ratio of carbon atoms to sulfate groups was 0.07.
The reason I asked that question was the sulfur zirconia has a whole lot smaller population of acids per gram of catalyst.
Right.
As opposed to zeolite.
Right. So you could be selectively poisoned.
Right.
Right.
So you would expect a much higher carbon content than the zeolite, even if the sulfur zirconia acid sites were covered with coke.
Right. Okay, and in fact, at this point, well, we thought about it. Let's see now, I'm trying to remember now. We had this scheme figured out for how to look for that. Clearly, we could do experiments where we try to titrate the acid sites that remain by base absorption, for instance. We haven't done that. And if it's the case that all the catalysis is being done by a very small fraction of the sulfate groups on the surface, then you're back to the age-old problem of how to find the active sites and how to identify whether what you're seeing spectroscopically relates at all to what is going on catalytically. What I can say at this point, of course, is that at least the spectra that we see and the phase changes in the zirconia that we see are consistent with the catalyst deactivating. Now, whether that's only part of the story or there's two stories or whatever, I can't say at this point.
I think the base absorption experiments would be good.
Would be good.
It would rule out the coking.
Yeah. Let me say one other thing. When this is another piece of information that's sort of hot off the press, namely, I was told this afternoon when I talked to Lee on the phone when we originally proposed looking at sulfated zirconium at PRF, we commented that we thought that the sulfate groups would be so-called resonance Raman enhanced because they absorb in the wavelength range, that is sulfate groups in solution or in compounds absorb in the wavelength range that is typical, where we're exciting with this 257 light. So Lee bought some zirconium sulfate because we don't see very strong signals from these sulfate groups, even though there's a fair number of them on the surface. And he told me today that the signal from the sulfate groups in zirconium sulfate are enormous. They're just giant compared to what we've seen from this catalyst. So his interpretation of that is that electronically, these surface sulfate groups are not like sulfate in zirconium sulfate, and they are not like sulfate ions in solution. They're something different, something unique perhaps to the catalyst surface. Again, it doesn't answer the question of whether only a fraction of them are active, or if they're all active, or those very tough questions.
Didn't you tell us that the sulfate disappeared on the H catalyst? And yet, when you
regenerate, it comes back, yeah. You don't lose sulfur, you just lose the sulfate groups, or they get transformed in such a way that they don't have the sulfur-oxygen double bonds anymore.
But Sockler uses a higher temperature than many others. Were these the ones that he's run at 300 or 325?
No, these were run at 180.
Okay.
I just have a question. If you have any plans of looking at coke on catalysts that have two uniquely different sites. I'm thinking like a bifunctional catalyst.
Sure.
Where people think that the coke on the metal is so much different than the coke on the acid.
Yeah, let me tell you where we are on that at this point. The initial thing that we want to do is we want to look at some standards. We want to get a feeling for how much chemical specificity we have with the Raman scalar. So Jeff Miller has made a whole series of USYs with various molecules absorbed in them. Monoring aromatics, benzene, toluene, some naphthalene, some hexene, cyclohexane, hexane, and so forth, so that we have a range of standard samples. He's done all the carbon-hydrogen analysis, and they've even done the C13 NMR to make sure that the molecules didn't get transformed in the process of being loaded into the zeolite. We want to look at all of those and see how much we can distinguish between these different molecules. Once we do that, I would like to go back to the coking study again, and to look at, I mean, there's lots of things to look at just within the zeolite. You know, what is the role of extra framework aluminum? I mean, the usual laundry list of things. What's the pore size effect? How does temperature affect things? What if we use different feeds for the coke? A lot of these kind of things have been looked at before, but the parameter space that people have been able to explore has not been very large, because the kinds of very laborious chemical treatments that people have done to try to diagnose the coke just can't be done very quickly. So this is a very quick way of getting some real, hard chemical information about how these various parameters are affecting the way the coke is formed. It may be the case that we'll never get beyond sort of, the four classes that I sort of laid out there. But I think even then, that we can contribute something useful to the role of these various characteristics of the zeolites in terms of what they do to coking. Now, once we've spent a lifetime doing that, then we certainly could look at the supported metals. The supported metals are interesting because they don't seem to coke the same way as the zeolite. We get this band at 1600 wave numbers, and you don't see the same kind of polymerization reaction at low temperature that you see on the zeolite. And I think that the interesting question then is what happens if you have both acid and metal? Now, do you see something which is a combination of the two, or how much interaction is there between those two things? And obviously, if we looked at each separately, then we would be prepared to say something about at least the issue of interaction. So, I mean, I think there's a lot that could be done, and I think that we won't be the only people doing this before very long.
Where have you found examples, or do you expect to find examples of the UV interfering and destroying what you're looking at?
Yeah, that's a good question. I don't have any examples at this point where we've seen the sample change on the time scale that we can measure one of these spectra. I expect that it will, I mean, one example might be, for instance, if we just have absorbed olefins, so monoolefins. Now with the UV, you have the potential of forming radicals, and then you might polymerize those olefins. So it might be that if we put the olefins down, so for instance on the platinum alumina, if we were to do that cold, so that the propylene was physisorbed on the catalyst, and then we irradiated, then it wouldn't surprise me to see polymer formed as a result of the photochemistry. So I think systems where you can produce radicals in the species that are mobile on the surface will be examples. So anything involving a chlorinated or a halogenated hydrocarbon would be a potential case.
What about inorganic metal oxides? Do you expect problems with them? And, you know, aside from carbon, you know, we folks that are doing oxidations.
Yeah. I don't know. I don't know enough about the photochemistry of those things. I mean, that was what I would do, is I would look first at the photochemistry and see how serious a problem the photodegradation of the materials is. I mean, certainly there are going to be cases where it's a problem. I know a little bit about molecular photochemistry. And I know that halogenated species are likely to be a problem with that. At least we don't heat the sample with the beam.
Okay, so I'd like to thank you very much for an interesting. I have one obligatory announcement before we adjourn, since we've had alcoholic beverage the agenda tonight. And that is, if there's anybody that feels that they've had too much, please see me and we'll make some arrangements. Help you home or to a hotel.
Well,
With that, I'd
we
like to
doing
thank
the
you for
hotel?
all coming tonight. Hope to see you again. I suppose it-
No, I'm going, Barbara and I go to the hotel.